Alice, and I work here at Cambridge University Press Bookshop. Most of the books we sell are aimed at grown-ups, but for the Cambridge Festival, I wanted to give kids a chance to quiz some of the brilliant experts who write them. I asked kids to send in their questions, and thank you if you were one of the ones who did. I got some brilliant responses. Then I put on my special interview jumper, jumped on Zoom, and asked them on your behalf. I had loads of fun doing these Q&As, probably because of all the cool questions I got to ask. There's a few little blips because we're all at the mercy of our internets. But I hope you enjoy them, learn something new, and feel inspired to carry on asking questions all your lives.
My name is Geraint Lewis, and I'm a professor of astrophysics at the University of Sydney. I am an astronomer and a cosmologist, and I study the large-scale aspects of the universe as well. And I'm very interested in the dark side of the universe, the dark matter and dark energy, which basically control the expansion and evolution of our universe. How I became a cosmologist is still a bit of a mystery to myself. I was interested in science when I was a kid. When I got to about 16, I discovered I could do mathematics, and I discovered that if you could do mathematics, you could do physics. And I sort of stumbled my way into a career whereby I study the mysteries of the universe.
Thank you.
I'm Luke Barnes. I'm a lecturer at Western Sydney University. I'm an astronomer and a cosmologist. So I think about the universe, and especially the universe on its biggest scales, and the things it does, like expanding and all that sort of fun. What got me interested in physics was that I was good at maths as a kid, and then sort of discovered that actually a lot of this maths you can apply to the real world. And that was pretty exciting, that you could write things on a piece of paper and work things out about the real world. And then within physics, discovered that astronomy and cosmology was absolutely fascinating. So that's what led me here.
So we've had loads of questions in, and they're actually pretty cool. I imagine I'm going to learn quite a lot from these. So the first question, we'll start with kind of Big Bang questions we had was, do we know what there was before the Big Bang and then how it happened?
I'll take that one, shall I, Luke? It's an excellent question, and there's a nice simple answer. The answer is nobody knows. We actually have a limit to our understanding of the mechanics of the universe at the most fundamental level. And because we haven't fixed all of that together yet, we just can't see what happened in the initial moments of the universe. So we don't know if our universe was born out of a true nothing, no space, no time, or if our universe is a connection or a continuation of a series of universes stretching off into the past and into the future. What we need lots of smart minds to come into cosmology and help us, because this is a big problem.
Okay, so I guess that kind of feeds into the next question, which is, if there are echoes of the Big Bang now, are there also echoes, therefore, of what came before it?
So by echoes of the Big Bang, we often mean something which is called the cosmic microwave background. And all that means is there's light that's come from the very early universe. So if I want to see something, I need the light to bounce off it. So if the light comes from that bookshelf over there, I can see it. There's light that's been traveling from very early in the history of the universe relative to how old it is now, but it's still about 400,000 years after the beginning. So that's not quite the beginning. Could there be echoes of what came before it? In a sense, yes, it's possible that there could be some sort of leftover evidence, like a fossil sort of left in the cosmic microwave background in the pattern. There have been some claims along those lines, not particularly convincing to most cosmologists, but it is possible that one day, we'll decipher there'll be some pattern that we overlooked there in the cosmic microwave background, which tells us something about the universe that came before.
Okay, next question. Did planets travel from where they were formed to the sun to make the solar system, or did they all start together?
So the sun and the planets were basically all born together. So our sun was formed when a big gas cloud collapsed. So this is how all stars are born. There's these really big gas clouds scattered throughout the universe inside these objects we call galaxies. And a chunk, roughly 4.5 billion years ago, fractured and collapsed down. And all of that material that collapsed down went in to form the sun. And leftover material, which was sort of orbiting around the sun, that condensed together into the planets. Now, the planets may have moved a little bit in their orbits. There's an idea that some planets can migrate from inner orbits to outer and vice versa. But they were all effectively born in a very small region of space.
Okay, thank you. Could there have been other Big Bangs, and could there be another one? And what would happen? And could there be different sizes of bang?
The short story is yes, there could have been. So there have been some ideas put around in cosmology where there were other Big Bangs, so other times when the universe was very hot and very dense in the past of our universe. So we know about one of them that we can sort of see the aftermath of. Maybe there were ones before that. And maybe there are other Big Bangs in the sense of the same, hot and dense bits of the universe that are expanding fast in other places. Maybe if you go far enough that way, 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 way off beyond what we can see, there's a bit of the universe which is right now, so to speak, undergoing its Big Bang. It would just be so far away that it doesn't really affect us. So those are two ideas that have been thrown around. Of course, we can't observe those unless the ones that came before us leave some sort of echo. And again, no evidence for that, unfortunately. But there are some ideas about how our universe works, which might have the consequence that some of those ideas are correct.
Okay. If there are parallel universes, does that mean that there must have been parallel Big Bangs all happening at the same time in the same way, or does one Big Bang cause multiverses?
Again, that's an excellent question. What we have to remember here, when we talk about parallel universes or when we talk about the multiverse, these are more of ideas than robust scientific theories. So when somebody says parallel universes or multiverses, there are different ideas embedded in those sort of concepts. So because we don't really have a single picture of all of this, there are different ways they could have been made. Now, there's some ideas that a multiverse could have started with one sort of uber Big Bang, and that set off the entire universe, and then chunks of this universe condensed out, and our universe is just one of these sort of condensed out pieces. There are other ideas where the multiverse is more complicated and there are universes being created left, right, and center. So there are individual Big Bangs going off, in this, it might be multi-dimensional sort of space where the universes inhabit. So all things are possible. These are mysteries that we need to solve. And I said, we've got this big problem in science to do with understanding what's going on at the very basic level to fix before we'll know the answer.
Okay. The next one is, how long did the Big Bang take, and was time even a thing then?
The problem with a question like, was time even a thing then, is that the word then means at that time. And so what you're trying to ask is, was time even a thing at that time? And it's really hard to think about that sort of stuff. But here's a rough idea. When there's basically a timeline, and here's us today, and we can keep going back in time towards a period earlier and earlier in the universe. And at some point, as Geraint said before, our ideas about how the universe works kind of fall apart. And so we can't even guess, we can't predict or extrapolate our ideas back even further. But in terms of how long did the Big Bang take, it's really, when we say the Big Bang, we just mean that in the standard way, the early universe was really hot and dense. But if we push way, way back, as far as any of our theories could possibly go at the moment, there is this idea that when we think about space and time, that we'll have to take into account something called quantum mechanics, which, depending on how you interpret it, says that fundamentally maybe time and space fundamentally, when we have a quantum theory of time and space, the time and space will turn out to be not a continuous thing, but a granular thing made up of discrete pieces, not perfectly smooth. It's very hard to think about those sorts of things. Was time even a thing at that time? But there are people trying to sort of put together, maybe time itself is not something fundamental. Maybe it's made out of something even more fundamental.
Okay. So now we're into black holes. So first one is, can we see black holes?
we can't see a black hole in itself because a black hole doesn't emit light, but because black holes have got strong gravitational fields, they pull on things very strongly. We can see their effects. So when we look into the center of our Milky Way galaxy in the constellation of Sagittarius, we know that right in the middle of our galaxy, there's something very, very massive, very, very dense, which is causing the stars that are orbiting it to go really, really fast. So the only objects that we have in our theories that can explain something that dense, that small, but so massive, are black holes. And black holes appear to be relatively common in the universe. There appear to be black holes in the centers of every galaxy, because everywhere we look, we either see stars whooshing around or gas whooshing around. And in fact, some of the most powerful objects in the universe, these objects called quasars, which are galaxies which put out huge amounts of light, more than all the light that comes from the hundreds of billions of stars they have from a tiny region in their center, they're thought to be powered by the effects of a massive black hole's gravity causing matter to move really, really quickly. So we can't see them directly, but we can definitely see their effects.
So the next one then was, can black holes move?
Yeah, absolutely they can. You can't push a black hole, of course, but for example, we're going around the sun thanks to gravity, and when you have sort of two things, one going around the other, that's nice and stable and great. If you throw in three similarly sized things all trying to go around each other, it all gets a bit complicated, and what can happen is two of them conspire to kick the other one out. And so it can be the case if we have black hole in a system where there's other things, the other two things might be two other black holes. They could be large stars, they could be anything. The other two could conspire to gravitationally kick the black hole out. And so there are people looking for what are called hypervelocity black holes, which are racing out of our galaxy extremely quickly, thousands of kilometers a second. So that's entirely a possibility. They're extremely rare, so don't sweat it. But yeah, black holes absolutely can move.
Cool. Thank you. The next one then is, can black holes die?
Yes, they can. And it's a very time-consuming process. So black holes, when they were originally sort of worked out mathematically, that was all written in a particular theory. That was Einstein's general theory of relativity. And in that theory, all it looks like is that black holes can grow. You pour mass in, they get fatter, and that mass can never come out. And that was a sort of picture until the 1960s and the 1970s, when Stephen Hawking was one of the first to ask the question of what happens if we combine Einstein's picture of gravity with this notion of quantum mechanics about what happens to individual atoms and space on very small scales. And he found that black holes aren't truly black because of the way that gravity interacts with quantum mechanics at the surface, at the event horizon of a black hole. Black holes actually leak energy back into the universe. And it's called black hole evaporation. But that leaking is really, really small. So they don't glow like you'd expect a light bulb to glow. They put out a tiny, tiny, tiny amount of energy. And that energy is coming basically from the mass that's in the black hole. So if we wait long enough, then the mass of the black hole will decrease because the black hole will radiate away the energy. And if we wait something like 10 to the 100 years, so that's 1 followed by 100 zeros, years, that's the kind of time scale that we need for the biggest black holes in our universe to basically completely evaporate away into nothingness. So we've never seen a black hole evaporate, but theoretically we think they can.
Okay. And you said something there which leads into one of my later questions, which was, what is the event horizon?
So the event horizon is the point of no return around a black hole. So as you fall towards a black hole, actually, for the most part, as long as it's a nice big black hole, you don't really notice that much. You're just sort of freely falling. But there's a point at which if you tried to get away, you wouldn't be able to, even if you're a beam of light. And so there's no sort of line in space that shows that point. But it's a very definite transition between the inside and the outside of a black hole. You could think of, it's a bit macabre, but if you're floating towards a waterfall and your boat can only go so fast, there's a point at which it's moving too fast for you to get away. But there's no line in the river that says that. So the event horizon is the point of no return. If no matter what you did, you turn your rocket on, even if you shoot, even if you're a light beam and you shoot outwards and you try and get away, the event horizon is the point of no return.
Okay. Fun one. What is it like in a black hole, and what would you experience in one?
So we can think about this as Luke just mentioned. When you fall into a black hole, if it's actually a big black hole, then you would fall in a long way and you wouldn't even know that you're inside. There might be other stuff raining down, but you would fall in and it would just be like being in normal empty space. Your view of the universe would start to become very distorted, though, because light rays that have also fallen into the black hole, their paths are now also being bent by the very strong gravitational field. So in a big black hole, you'd fall in, your view would be a bit strange, but things would probably be okay. But as you get closer and closer to the center of the black hole, this place called the singularity, what happens is the gravitational fields, they build very quickly. And if you imagine that you fall in feet first, what you suddenly find is that the gravitational pull on your feet is considerably bigger than the gravitational pull on your head. So what that means is that your feet are being pulled harder than your head, so you're going to be stretched in this direction. And you also get a compression in that direction as well. So you actually get drawn out and drawn out and drawn out, a process which physicists call spaghettification, because this is what happens to you. You'd get drawn out, and then bad things happen, right? So your body can only take so many forces, and you would be destined to end up on the singularity where all the mass is. Now, on a big black hole, that might take a while. On a little black hole, they're even deadlier because the gravitational fields change very, very quickly there, is that you would probably feel that difference in pull, even before you fall through the event horizon. So yeah, they're generally not good places. I wouldn't advise going on one for a holiday.
Okay, I'll take that into consideration.
Yeah, not that anyone can go on holiday.
No, I know. Well, probably COVID-free in a black hole, at least.
Yeah.
Okay. Could you time travel using a black hole? And then if you personally could time travel, would you do it?
So here's the interesting thing. What was discovered was if you make a black hole rotate, even weirder stuff starts to happen. So what we've been talking about so far is the sort of normal black hole that's not rotating, but actually rotating something a black hole could easily do. That point at the center where it all goes to who knows what, actually now becomes a ring. And what you can do is if you hit the ring, bad luck. If you miss the ring and go through it and back around, you can actually arrive back at not just the place you started, but the time you started as well. So you can time travel, but only back to the point at which you first entered the vicinity of the ring itself.
Okay.
In particular, you can't necessarily get out of the black hole to tell anyone about this. But as one textbook I like explained it, you could play poker against yourself. So you could sort of meet other versions of yourself. Weird stuff like that happens around a black hole. If you could time travel, would you do it? Well, I suppose I might, at least to find out whether it could happen. That would be interesting.
Can I add another bit of an answer there?
Yeah.
So you can actually use the black hole to travel into the future, by basically flying down towards the event horizon, hovering, which is going to take a lot of rocket power, and then flying back out again. Now, if anybody has seen the movie Interstellar, there was a thing in there about this entire concept of time dilation, that time goes differently depending upon where you are in the vicinity of a black hole. So if I could go down close to the surface of a black hole. I could spend a year there on my time. And when I fly back out again, then maybe 1,000 years has passed in the outside universe. So I could have jumped 1,000 years into the future. Would I do it? I would. Yes, I would. I would definitely do it. I would time travel backwards, forwards, sideways. I would love to explore history.
So on black hole travel, could you travel to other dimensions using black holes?
Other dimensions is not, well, there's a bit of talk of that in physics in a couple of different ways. So we're familiar with a three-dimensional world and then one dimension of time. One of the things that was discovered sort of in the 1920s-ish was that interesting stuff happens in the laws of physics if you assume that there are more time and or space dimensions that we can't see. If you pull on that thread, then here we are sort of 100 years-ish later, and there's all sorts of ideas about strings with multiple dimensions and vibrating and all that sort of stuff. In some of these ideas, there would be something like traveling to other dimensions using black holes. It might be a black hole solution. You might be sort of more talking about what's called a warp drive, sorry, a wormhole, which again, Interstellar explains. You fold the paper over and you put the pencil through the paper. Those sorts of things happen in normal general relativity. And if you extend it in this way where there's other dimensions, you could have entire dimensions, you know, three-dimensional world over here and another one over here and some sort of path between them. That's some really weird and wacky physics, but that is being sort of talked about out there.
So next then, when will the sun die, and when it does, will it become a black hole, and how much of the solar system will get sucked in?
Okay, talking about the death of the sun, that sometimes makes people very sad. So let's hope that when it happens, you know, humans have developed spacecraft and we've flown off and we've found other planets. But the sun, of course, is a star, and the sun is powered by the nuclear reactions going on at its core, and it's only got a certain amount of fuel. Okay, so there's a finite amount of fuel, and the sun, once it's used up that fuel, that's essentially it for the sun. So the sun is roughly halfway through its life. So it's about 4.5 billion years old now. It's got about another 4.5 to 5 billion years of life left in it. That sounds like a long time, but the sun is slowly getting brighter. So it's getting brighter and brighter as it ages because its internal composition is changing because of the nuclear fires. And I'm not sure exactly the number, but I think in about 2 billion years, the sun will have got hot enough that you wouldn't be able to have any life on Earth. Essentially, the radiation from the sun would blow away the atmosphere, it would boil away the oceans. And as you can imagine, that's not going to be a great place for a holiday. But that's not the end of it. So one thing we do know is that the sun is not going to become a black hole. What dictates whether or not a star becomes a black hole is how massive it is. So the more mass you have, the more gravitational oomph you've got. And so big stars, 8 times the mass of the sun, when they die, lots of stuff happens and they can form black holes. The sun, though, will do something quite different. Once the sun uses up its hydrogen in its core, which is its main fuel, it then goes on to basically snack on the next element available, which is helium. And that really changes the way that the sun behaves. And what actually happens is that the sun starts to grow. It grows and gets cooler. So the sun will get bigger and bigger and bigger and cooler. So it goes from being the white color it is now through orange, and it will become red. So it will grow and grow and grow. And it will firstly basically get larger than the orbit of Mercury. So Mercury will be consumed. Then Venus will be consumed. Then the Earth will be consumed. And some people think it might even get out to the orbit of Mars. Okay, so the sun will become this red giant star. Nearing the end of its life, right, the sun, it'll become somewhat bad-tempered. You know, you do as you get older, right? You just get a bit grumpier. And actually the sun will actually start to pulse. It'll start to beat in and out. So it won't be a fixed size. It will oscillate in and out. And those oscillations will become more and more violent until there's the last sort of puff, and the atmosphere of the sun will break away and be pushed off out into space. And if anybody listening is an amateur astronomer, they may have seen these. These are called planetary nebula. They've got nothing to do with planets. They just look like circles on the sky. These are the outer layers of stars which have been blown away. And what would be left, our sun will be a small little star. It's basically its leftover heart, and that will be what's known as a white dwarf star. And so the sun will end its days over the next many billions of years of this little white dwarf core cooling down and cooling down.
Cool, that's fun. Right, so next then, if stars get sucked into black holes, do they become black holes inside black holes?
No, they don't, unfortunately. So we mentioned spaghettification, and that's going to happen to anything that falls into a black hole. And we said that if for a very big black hole, like the ones we think we see at the center of galaxies, you could cross the event horizon and not really notice. But even then, your time before you hit the center is still only measured in hours. So a star's going to suffer the same fate. It'll get sucked in. It'll sort of, if it was a huge black hole falling into, it would sort of elongate a bit as it crossed the event horizon. But eventually that spaghettification is just going to stretch it out, and it's going to feed into the singularity, whatever happens down in there. So unfortunately, no, you wouldn't get black holes inside of black holes.
Okay. So the next one is, why is space black?
Why is space black? Now, that is a really good question. So this is something that has bothered astronomers for a long time. Initially, right, because we used to think, a few hundred years ago, that the universe was infinitely large, going off in all directions, and infinitely old, right? Before people thought about the birth of the universe and the Big Bang, we thought that the universe had always been around and it was infinitely big. And if you have a universe that's infinitely big and you've got stars scattered everywhere, then everywhere you'd look, eventually you would see a star. And so we would expect that if the universe was infinitely big and infinitely old, that the sky should be as bright as the surface of the sun and not dark. So this is something that's known as Olber's paradox. Why is space dark? And what we have now realized, of course, is that one of those ideas about the universe being infinitely old is incorrect, right? The universe has only been around for roughly 14 billion years. So there hasn't been time for light to arrive from all of the potential stars out there in the universe. So for us, the sky being dark is because our universe is only 14 billion years old. But it's a pretty deep question when you think about it.
Okay. Then, what is dark matter, and is it the same as the bits of the universe being missing, and how do we know?
So dark matter, as an astronomer, if you want to see something, it's got to be really bright, because we're looking at things that are a long way away. So stars are wonderful, nice and compact and small and put out lots of energy. If there was a form of matter out there that wasn't shining really brightly, it would be really hard to see. And so the question we have when we look out at the universe is, there's the light that I can see. How much of that light is telling me about matter in the universe? Or to put another way, for each bit of light that I see, how much stuff is there? And one of the things we've discovered is that we can sort of measure how much stuff there is by how things are moving around it. So Geraint mentioned before, we can see things move around black holes, for example, because they have a gravitational pull. When we apply that to, say, galaxies as a whole, what we find is that if all of the matter there was just the stuff that's shining brightly at us, or the stuff that we can see and account for, there wouldn't be enough gravitational pull to hold this thing together. So what we think of as a galaxy going around would actually be a galaxy in the process of just flinging itself into pieces. So because we don't think that, one of the options that seemed likely to us is that there is this other form of matter called dark matter. And as we've looked around, we found evidence of that in different ways. We see evidence of it in the way that light bends as it travels to us through the universe. We see it in the cosmic microwave background. Again, not directly, we see evidence of its gravitational pull. As well as that, we think that dark matter is not the ordinary stuff around us. It's not just the stuff of protons and neutrons and electrons in the periodic table, but just out there somewhere. It's actually made of something different. As well as that, there's some of the ordinary stuff like us, which is just dark. It's just not lit up. And so finding that's a challenge for us as well.
Could I just quickly add as well on top of that? So part of the question is, do we know what dark matter is? And the answer is no, we don't. So we think it's, as Luke mentioned, we think it's a particle. It's a member of the electrons and the quarks and all that stuff on the very small scale. But we just don't know. We haven't got a space in our theories which naturally explains the stuff that we see in the universe. So this is a big area of research at the moment to just tie down what is dark matter.
Can you weigh stars and galaxies?
The short answer is yes, but obviously not by any sort of direct means. So, for example, we can weigh the sun by looking at the pull that it has on the planets that go around it. And so if we work out planetary orbits and all those sorts of things, we can, because we can understand those in equations, we can find that number in the equations that stands for the mass of the sun. And it takes a bit of hard work, but we can do it. And so similarly, we can do this with stars and galaxies. With galaxies in particular, we can, they also have, rotation. They can, the stars and planets are going around, so we can use that motion to infer how much stuff there is holding everything in together under gravity. That's how we've sort of found dark matter. And with stars, it's a little bit different, but as we model how stars work, as we get a good sort of equations that describe how stars work, again, that will depend very crucially on how much stuff there is, which determines how strongly everything is squished together, how strongly those nuclear reactions have to react to that, and pressure holds the whole thing up, and you make a model of that. And again, as a part of that out comes the mass of the sun, depending on again, we can infer that from observations that we make. So not directly, but we can understand the universe to a sufficient degree that we can work out what the masses of these things are.
How far into the universe can humans see, and what's the furthest a bit of Earth tech has gone?
Well, with your naked eye, you can't see, well, actually, with your naked eye, you can see about 2 million light years into space. So with your naked eye, you can see the center of the Andromeda Galaxy, which is the nearest big galaxy to our own. And the light from that galaxy left roughly 2 million years ago, before there were humans really walking on the surface of the Earth. But with our telescopes, we can see much, much further. And we are now, it depends on which wavelength we look at, because that reveals different parts of the universe. Luke mentioned the cosmic microwave background radiation, which comes to us from all over the sky. But that light has been traveling for over 13 billion years, almost 14 billion years to get to us. So we can basically see as far as we can see in the universe, because the cosmic microwave background is that limit. What we are doing now, it's not really about the distance, it's about trying to see how faint we can go, because that reveals very distant galaxies and things going on in the early universe, things where light had to spend a long time traveling towards us. So this is why we need bigger and bigger telescopes, is because we want to try and spot the fainter and fainter objects. But we've seen as far as we can see. It's now just filling in what is in between us and that limit.
That is the end of my questions. Thank you. Thank you both for answering them so well, and I could even understand them. So that's
good.
great. Thank you.
You have some great questions.
Cool.
Oh, thank you for inviting me. There were some really great questions there about the universe. And look, I'm more than happy to answer questions about space, life, the universe, and everything again in the future.
Cool. Thank you very much. The next question gets a bit metaphysical, which is, do you think God and science are incompatible?
I think we may have to ask us both separately about this one, because we might have differing opinions.
Yeah, exactly. It's something that certainly people have taken longer than a Zoom call to cover.
Yes, yes. From my point of view, I guess it depends on how you define the word God, right? If God is meant to be this overarching being that has control over the universe, then that doesn't gel with the scientific ideas of how we think the universe behaves. Of course, there are ways around it. You could say God wrote down the rules of the universe and then went off to do something else, and the universe just does what it does on its own. So, I think that kind of notion of this omnipotent being and the notion of science as we want to understand it do not basically go together. But that doesn't mean that lots of scientists aren't religious in a sense. And I think, of course, there's that more personal view of a God. So, you know, the whatever gets you through the night kind of aspect of what brings you comfort in the universe. Of course, that side is doesn't necessarily intrude on the scientific side. So, yeah, it depends what you mean by God. And I should put my cards on the table that being an atheist, I have no need of this hypothesis or whatever. Somebody put it that way in the olden days.
Laplace.
Laplace, that's right. So I will hand over to Luke to give his viewpoint.
So very much the opposite viewpoint over here. So my cards are all the theist cards. There's a third option there, which is that the laws of nature just are describing the way that God runs the universe. And so you need neither an absent God nor a sort of self-sufficient nature. There's an analogy here, which is not a great analogy, but it'll do for the moment, with sort of a character in a video game trying to work out the rules of their own universe. So there would be the rules, their science of Mario trying to work out what the blocks are made of and what happens when you jump over here, versus then the top down, someone wrote this whole thing. But then, so I would say that's just pure barest compatibility in the sense that they aren't directly contradictory to each other. That's whether you want to say that there is or isn't a God after all of that, whether there's anything useful for God to do, is a question we talk a lot about in that book, by the way, A Fortunate Universe, Cambridge University Press, but which we have different conclusions.